And that's it. So let's get back to our slides. Okay. We have opened the microphone, right? Yes, we have. So unless something is wrong, everyone should be able to hear me. Error handling. The main idea is when you want to know how a system call behaves in the case of an error, when you want to know how a system call behaves in terms of what parameters it accepts, what are the types of those arguments, how it operates on those parameters. If there is anything you want to know about the system calls, what you do is you simply check the MAM page of that system call. There is a MAM page for every single one of them, and you do not even have to be online to check it. You simply open your terminal and you type man space the name of that system call. And there, especially as far as errors are concerned, you will see at the return values subsection that it will be mentioning in which cases it returns an error and exactly what it returns in order to uh, pass the message of which error exactly. Now, when a system call fails, it sets, of course, the global integer variable erno to a positive value that identifies the specific error. So, I don't know, 1, 2, 3, 4, 5, whatever, in order to specifically notify the person that called that system call so that that person will know what exactly went wrong. If you want to benefit, if you want to use the erno variable, all you have to do is just include the erno header file in your program. And then, of course, you will be able to access the declaration of erno as well as some other constants for the various error numbers. Now here, for example, we have a well, somewhat standard way of calling the read system call. Now the read system call reads from a file. It reads num bytes, and it places those bytes into a buffer pointed to by the second parameter boof. So it returns the CNT value, which is short for count, and normally it should be returning the number of bytes that it has read successfully. So if it returns -1, that means something went wrong. So that means if you want to know what went wrong exactly, you must check the value of erno. Here, for instance, we do it in a bit of a clumsy way. So we use simply an if clause in order to check whether erno is equal to one of the standard errors. So this is a standard error number, the inter, which signifies operation interrupted. And if that is the case, it simply prints on screen. It prints on the standard error file, which usually points to the screen, that the read system call was interrupted by a signal. Here, of course, we should be tabulating. Otherwise, if CNT is not equal to -1, well, in that case, it might have been successful or something else might have happened. Or let me check it. No, the else is inside. I'm sorry for this. The tabs have been indented falsely. So if erno is not equal to the interrupt message, well, in that case, the read system call, of course, can fail due to some other reason. Maybe the file that we're trying to access is not present. Maybe we don't have the correct permissions, and so on and so on. So that means since we do not have access to the exception handling mechanisms that are available in the Java and C# and in Python, well, here we have to simulate it on our own. And depending on which error has taken place, we will take the appropriate action by checking each and every one of them. An important note, when checking for an error, one should always first check if the function return value indicates an error, and only then examine erno to determine the cause of the error. Otherwise, if, for instance, we go directly into checking the value of erno, in that case, the situation that your colleague has mentioned before the break can happen. So maybe read the system call has succeeded. So it has returned the number of bytes that it has read. And errno has not been set. But that doesn't mean that errno has an empty value. It doesn't mean that it is initialized to 0 in those cases. It will still contain the value of the last system call that failed. So long story short, first check whether the system call failed. And if it has failed, only then examine the value of errno. As simple as that. If you check the header file at the bottom of the slide, you will also see the list of possible errno values and the related messages. Now, what is the proper way of handling the errno value? I mean, are we supposed to just check with if clauses, errno equal to this, errno equal to that? No, it's not like that. A common course of action after a failed system call, of course, is to print an error message based on the errno value. That is one of the most frequent reactions that we have to errors that take place within our programs. A system call fails, we print it on screen, and depending on its level of seriousness, we might or might not terminate the program. So what is the proper way, the standard way of checking the errno value and printing messages? Well, you can use the perror and str error library functions, not system calls, library functions that are provided for this purpose. What does perror do? Perror is very simple. It is available from the standard input-output header file. Maybe you have used it already, I don't know. It prints to the standard error file, so it prints to stdr, always, the string pointed to by its message argument. So whatever you give it as an argument, it will print that. For example, an error has happened. For instance, I don't know, something happened, etc. And it will concatenate it right after it, automatically. It will include the message corresponding to the current value of errno. So let's say that you try to open a file. You could not open the file because the file cannot be found. You call perror and you give it a message of error. What will perror print? It will print error, and after it, it will include the message file not found. str error, on the other hand, it receives as input the value of errno, and it returns the string corresponding to it. So you give it the errno value, I don't know, 36, and it returns file not found. You give it 53, and it returns the corresponding message, not enough memory, and so on and so on. Example, here we have in our main file, we call the fopen library function. Be careful, this is not a system call, but we know that behind the scenes, fopen is using open in order to open file.txt in read mode. And we know that if open fails, the system call fails, it will return -1, which means fopen will return null. So in the case of an error, we check whether that error took place or not. And then we use perror in order to use the errno value automatically and print a nice explanatory message on the monitor, the standard error device. After which, since we cannot open the file, we have chosen to terminate the program by returning from the main function. But please pay attention, we are returning with a status value of -1. Whereas if it had been successful, we would have returned with a status value of 0. So remember, 0 is reserved for successful completion, başarılı tamamlanma. 0 is reserved for successful function calls, successful programs. Negative values for errors. Please do not change that standard. Please adhere to it as much as you can. And at the bottom, we have the standard program output. Any questions so far?
Yes, sir.
Please.
Since we need to write the p error message string ourselves, does that mean that we need to memorize all the enumerated values of errno and?
Don't, be careful. Be careful. You do not need to memorize anything for perror. The message that you give to perror is only. Look at this example. We only gave it error and 2 dots. But what did it print? Error 2 dots. No such file or directory. I didn't tell it which error happened. I just gave it the initial message, and the rest of it was completed by Peror automatically. So you do not have to memorize anything.
Okay.
So that's why we have Peror, so that it will do it in our place. I only give it the initial prefix of the message. For instance, I could use a timestamp. I could write, for instance, 10th of March, 9:43, two dots, no such file or directory. Or I could include the name of the function. So in function main, at this date and time, that's it, the message. And then it will concatenate it with the corresponding errno message. That's why it allows us to include a message in the beginning.
Thank you.
No problem. Other questions? Okay, so that means in case of errors, what do? Number one, check whether the system call failed by checking whether it returned -1 or not. And if it is returned -1, use peror and or str error in order to check what exactly has went wrong. And depending on the type of the error, maybe you can do something about it, fix it somehow. Or if you cannot fix it, then you print a nice message, an explanatory message by using peror, str error, or whatever you want. And then, if necessary, you exit the program after having freed all the available resources. This is what we call an elegant exit. Zarif çıkış. This is what we call an elegant exit. Print the, let the user know what was the source of the mistake, free all available resources, close file, free allocated memory, etc., etc., and then exit with a negative value so that the person that called the program will also know that it has failed. That's what we call an elegant exit, and that is what is expected of us. What is the opposite of an elegant exit? The opposite of an elegant exit is you do not check whether it failed or not. You just let the error propagate. You try to allocate memory, but you have no idea whether it succeeded or not. So you end up with a segmentation fault afterwards, and the program exits abruptly. You do not free any resources explicitly. You delegate that responsibility to the kernel, and the user has most of the time no idea what went wrong. That is the opposite of an elegant exit. That is a very rude exit. So make sure your exits are always elegant. If they are not elegant, you will lose marks. Some more error handling. By the way, which slide are we? Just in matters of organization, we are at number 17. Okay, that's good. The various library functions, of course, return different data types. They might return integers, they might return pointers, etc., etc. Library functions, not system calls. The various library functions return different data types and different values to indicate failure. Now, for our purposes, library functions can be divided into the following categories. Now, what are the categories of library functions? We know that system calls use errno, but do the library functions also use errno? Well, some library functions, they behave exactly as system calls. In other words, they return error information in exactly the same way. So a -1 return value with errno indicating the specific errors. So you can diagnose them in the same way that you diagnose system calls by using peror and str error. However, some library functions return a value other than -1 on error, but they still set errno in order to indicate the error condition. So that means these functions, they deviate a bit from the standard. What is the standard? Return -1 on error, 0 on success. But since they still set the errno variable, that means you can still use peror and str error functions in order to diagnose these errors. And of course, there are also some library functions that don't use errno at all. The method for determining the existence and causes of errors depends on the particular function and is documented in the function's manual page. For these functions, you must not use errno, peror, or str error to diagnose these errors. Long story short, whenever you call something custom, we are recording, right? Yes, we are. Whenever you call a custom function, so a library function, not a system call, you must always make sure to have studied how it behaves in case of an error so that you can take the proper precautions. Of course, you might say that you can omit it. Maybe it is a function that fails very, very rarely, such as, I don't know, malloc, for instance. It doesn't fail really that often. I mean, we usually have enough memory to allocate a few arrays. But if you want to do this seriously, if you want to exercise this professionally, well, in that case, this is a way. The method, the way of calling system calls is to check the return value. -1 on error, 0 on success. If an error, check errno. If the errno is not set by the system call, it is always set by a system call, but if it is not set by the library function, then you must make sure that you have checked its manual pages in order to figure out how it behaves in the case of an error. You need to make sure that there is no leak left. And by leak, I mean unchecked error situation, not a memory leak. Of course, you must also check for memory leaks, but you must make sure that there is no unchecked error situation. What happens if you leave an unchecked error situation? For instance, a function call that for which you do not check whether it has failed or not. Well, in that case, you will be faced with bugs that are very difficult to debug, and it will be your time that will be wasted. And often this leads to bugs that are very difficult to diagnose. So be careful with it. It's very simple, but it can save you a lot of time. And now, of course, we are leaving error handling behind, and we are switching to processes and programs. What's the difference between a process and a program? A process is an instance of an executing program. A process is a program that is in the course of execution. So you can execute the same program multiple times. So you can have multiple processes executing the same program. That's possible. There is a question. Mr. Patolu says, why Peror doesn't return a string with the cost function's name? It could remove the conflict. Which conflict? You already have str error, which converts errno to a message, to a string. Well, Mr. Yusuf, I will let you write about that conflict because I didn't understand what you mean by conflict. So anyway, let's. If I'm using Peror for checking that function, which doesn't use Peror, for example. So there is a function that you have called that doesn't set errno in case of an error. So you're saying that in case you call Peror by mistake, in those cases, it should print a string that also includes the name of the function that involves that error. Well, there are several things that can go wrong there. For one, for instance, let's say that you call fopen. Fopen inside it uses the system call open. So if there is an error stemming from there, it might print the name of the function that took place internally. So number one, the name of the function that you might see there might not correspond to the function that you have called. So it might correspond to something that is called internally, and you will have no idea where that internal function takes place. So let's say that you have 10 functions there, and they call other functions inside them, which call other functions inside them, and you will have no idea from which layer that error comes, even if you had the name of the function there. And second, well, this is basically the tradition. I mean, if you have a library function that doesn't set errno, then it is your responsibility to know that it doesn't set errno and that you shouldn't be checking the value of errno. So that is a responsibility that has been delegated to you. I mean, that is the main philosophy of both the C library, of both the C language and the POSIX standard in general. It is completely the developer's responsibility to get these things working. For instance, C doesn't care if you don't pay attention to types. If you try to set, for instance, a float inside an int, or if you call malloc and you do not pay attention whether the memory has been allocated or not, it is completely your responsibility. And just like C doesn't care about your mistakes, and it is the developer that pays for those mistakes in tears and sweat. And that is the philosophy of the POSIX standard too. It gives you the necessary information. It tells you, look, this system call will set errno, and you can trust it to set errno, so you can use perror. But this one, this library function, does not set errno. So if you try to use errno still, if you try to still use perror in order to diagnose the mistake, well, that is your problem. I mean, that's the philosophy of the POSIX standard. But as I said, even if they tried to include the function name there, since it could be originating from a function inside the function, inside the function, inside the function, and it might have a name such as my favorite function 231, you would still have no idea where it was coming from. You would have to go inside the source files in order to figure out which of the functions that you called contains a function named my favorite function 231. So it will be very practical. Processes. A process, an instance of an executing program. And as we said earlier, of course, a program can be executed multiple times. You can execute Firefox 10 times, and you can have 10 windows for Firefox, each with multiple tabs. So that means you have 10 processes, each executing the same Firefox program. Now, what does a program contain? If, for instance, you look inside a binary file, you can use, for instance, the file command for that. I recommend that you do that on your terminals. I would have done it too if I had access to a Linux terminal right now. Now, the file command will also show you that, but a program contains all the necessary information that the operating system needs in order to convert that program into an actual working process. Now, what do you need? Put your place in the shoes of the operating system. There is a program, an executed, compiled program, ready to execute. What kind of information do you need in order to execute that file? One, you need to know what is the format of the executable file. What is the internal organization of that exe file? So you need some kind of an identification in the beginning. So if it says, I don't know, if it contains a certain number, that means the organization is first code, then entry point address, then initialized data, then uninitialized data, then constants, etc., etc. So you need somehow a number to identify its internal organization. Then, of course, you definitely need the instructions that you need to execute in order to, execute the program naturally. So you need the machine language instructions. And of course, you will not modify them in any way. You will just read them from the file and immediately place them into RAM, into memory. And then one by one, you will take them to the CPU from random access memory. But of course, you also need to know the program entry point access. Just because a program has 1 million instructions, it doesn't mean that the program will start from the first instruction. So you need to know where from it will start. So the entry point address. And of course, then we have the data. You can have global variables that are initialized, such as constant strings. And you can also have global variables that are not initialized, for instance, an array of integers. All of these must be contained in that executable file in a certain order, and it is up to the operating system, whenever you execute them, to read that file, transfer all of that information to memory, and organize a section of memory, so allocate a part of random access memory, so that it will place that code there and start the execution from the entry point of that program and place the initialized and uninitialized data of that program to the corresponding memory locations. What else do we have inside that file? Well, we also have symbol and relocation tables. What are these tables? These describe the locations and names of functions and variables within the program. So let's say that you have a function named, I don't know, my second favorite function. Well, it also needs a table that it will use in order to figure out where, in which instruction that function starts. Just because we have names for our function, it doesn't mean necessarily that the operating system will behave in that way while executing it. Instead, it will have code names for those functions. These tables are used for a variety of purposes, including debugging and runtime symbol resolution. But beyond those relocation and symbol tables, there is also, of course, shared library and dynamic linking information. So let's say, for instance, that you're calling printf. Where is the code of printf? Is it inside the executable file? Of course not. Printf is available as a dynamic library from the standard C library function. So when you execute that file, you also need to include that information. So if somebody calls the function printf here, where is it supposed to find printf? So you include that information. Printf is available in the standard C library function, version something something, location, etc., under /lib/ etc. And of course, there can be also other kinds of information in order to help construct the process. Bottom line, one program may be used to construct many processes, such as the example of, I don't know, the Firefox or Chrome or whatever, or many processes may be running the same program, same idea. So just because you have a single instance of a single Firefox executable, it doesn't mean that you can have only one process of it. Now, from the point of view of the kernel, a program is an actual thing. It's an actual file, an actual executable file, a binary file that exists on the hard drive. A process is more of an abstract entity. Biraz daha soyut bir kavram. It is defined by the kernel. It is the kernel that defines the process. And in order to convert the program into a process, of course, it needs to allocate resources. It needs to allocate memory. For what? In order to place the code of that program, in order to place the global variables of that program, in order to create the various kernel data structures that it will need, that the kernel need in order to manipulate that process. What kind of data structures? Well, it will need a table to hold the pages of memory allocated for this process. It will need a table to keep the open file descriptors, the files that have been opened by this process. It will need a table to store which signals are supposed to be handled and delivered to this process. It will need some data structure to hold what is the current working directory of this process, and so on, and so on, and so on. Things about inter-process communication, things about synchronization, and so on. And all of these, of course, are specific to each process. There is a different data structure, for instance, for the open file descriptors and so on, for every process. And that means it will be stored in the memory area that has been allocated to that process. So for every process, you have inside it, in that memory region allocated to it by the kernel, you have the code of that process. You have the various kernel data structures that are necessary for the logistics of that process. And plus, of course, you have the memory area in order to hold all the variables, the global and local variables of that process. And since you can have hundreds or thousands even of processes on a common running system, of course, you need to somehow identify them. And the standard way of identifying a process is the process ID, short for PID. Now, the PID is a positive integer. It starts from 1, not from 0, basically. And it is used to identify uniquely the processes that are running on a system. If a process calls the getPID system call, it will return as an integer value the process ID of that process. Now, something very interesting about the system call is that it always successfully returns the process ID of the caller. It cannot fail. So there is no meaning, there is no reason for checking whether getPID has returned -1 or not. It cannot fail. This is an exception. Most system calls can fail. It doesn't receive an argument. You need to include the Unix standard header file in order to be able to use it. And that's it. whenever you call it, it will return the process ID of the process that executed the system call. But of course, every process also has a parent. And by parent, I mean the process that created it. Because in the beginning, when you boot your system, there is only one process, and that process is init, which has a process ID of 1. And it is that process that forks and creates the second process. Then you have two processes while booting. Then the second process can start a third process. Then init can start a fourth process. The fourth process can start the fifth process, and so on and so on. And thus the process IDs increase. So whoever created that process is considered the parent of the child process. And how do you access the ID of the parent process? Simply by calling get parent process ID, which also requires the Unix standard header file. And of course, it returns the process ID. And similarly to get PID, get parent process ID also never fails. It also always succeeds and returns the process ID of the parent process. Now, do the process IDs increase indefinitely? No, they don't. There is a maximum allowed process ID, which is often at approximately 65,000, approximately 65,536. And whenever you reach that point, so you keep creating processes and processes and processes, keep creating them, so the process IDs increase. Once they reach that maximum value, which happens very rarely, it wraps up to the beginning, but it doesn't wrap up to 1. It wraps up to a number that is a bit higher than 1, such as 300, 400, and 500. Why? Because the initial few hundred processes are usually reserved to the kernel. And of course, whenever a process terminates, that process ID becomes free again. So let's say that you had a process working with process ID 1500. Then you create a new process, which has a process ID 1501. But if the process that had the process ID 1500 fails, that means that process ID is once again available. So if you create a new process, will it take 1502 or will it obtain 1500 as a process ID? It will receive 1502. The process IDs always increase, and they only return to the beginning. They only wrap up after reaching the maximum number of process IDs. Any questions so far? Okay. So let's say that a process started a new process. So a parent now has a child process. The parent process has a process ID of 1000. The child has a process ID of 1001. So if the child process calls get parent process ID, it will return 1000 because that's the process ID of the parent process. If, however, the parent process terminates before the child process, that means the child process has become an orphan. Öksüz kaldı. And what happens in that case? So since it doesn't have a parent, what happens if we call get parent process ID? Whenever a child process is orphaned, so in other words, its parent process terminates before the child process, it is immediately adopted by the init process. So that means if it calls get parent process ID, it will return the process ID of init, which is equal to 1. Now let's look at something more interesting. The memory layout of a process. How does the operating system organize the memory? In which sections does it organize the memory of a process after reading it from the hard drive and placing it onto memory? Now, this part of the course is, of course, explained in much more detail in the operating systems course. So this is just a reminder, basically, in order to fill in any missing details and so on, because it is not really our job in this course, our objective to teach you the principles of operating systems. Our job is to write programs that exploit this organization. So we are just going over them superficially, and we leave the detailed examination to Yusuf Sinan Hoca in the context of the OS course. But just to make sure that we are all on the same page, let's look at those segments. Now, the memory allocated to each process is composed of a number of parts, naturally, and the proper terminology to refer to them is segments. So the memory area of a process is divided into segments. Türkçe bölütler. Segment, bölüt. What are those segments? Now, the most usual one is the text segment, and do not be fooled by the name text. It basically means that that segment contains the CPU instructions of that program, from the first one all the way to the last one. And it is definitely a read-only section of memory. It has a certain flag, that segment, that makes it read-only. So even if you try to modify, either deliberately or intentionally, the code in your program, you can't. It's forbidden. This is something, for instance, malware and viruses attempted to do in the past in order to disguise themselves. So first the program is copied from the hard drive to the random access memory, and then the program, while it is executing, it starts to modify its own code while executing. Now, this is, of course, very dangerous because then it can do whatever it wants to, basically. But this is not possible in a POSIX operating system, in a POSIX compliant operating system, because very simply, once a program becomes a process, it is forbidden to modify the section of the memory, of random access memory, containing the actual CPU instructions. So whatever was written in that exe file, in the hard drive, those are the instructions that are going to be executed, not something dynamically generated at that moment. So this is important in the name of security. Another segment is, of course, the data segment, which is divided into two, the initialized data segment and the uninitialized data segment. Now, both of them contain global and static variables. But the difference is, of course, the first one contains the initialized ones, and the second one contains the uninitialized ones. Of course, you have the stack. A portion of memory is allocated to the stack, which is a last in, first out, of course, as you know, data structure, which is used in order to store all the local variables, the function parameters, the function return addresses, and so on. And it is highly dynamic. The more functions you call, it keeps on growing. The more you return from your functions to the main function, the more it shrinks. And of course, finally, we have the heap, which is the segment of memory, which is allocated for dynamic memory allocation. So every time that you call malloc, calloc, realloc, this is where from you obtain those bytes of memory, from the heap, not from the stack, not from the data segment, and definitely not from the text segment. Any questions so far? I guess this is not really that new to you. Excellent. In case you have questions, do not be shy. You can always type them in. Or if you are too shy, you can always send me an email. Let's look at an example. Or let me ask a question. Why not? What's the difference of global and static variables in C? Can anyone answer that? What is the difference of global and static variables in the C programming language?
Can I answer? Sir, can I answer?
Yes, Mr. Jan.
The statics are unable. We are not unable to manipulate the static values, but the globals are can be manipulated by other functions easily.
So we cannot manipulate the values of static variables.
Yes, we can, but
we can. But
we can't do it in local functions, etc., and some methods.
so we can. Okay, so the difference is that we can modify the values of static variables, but cannot modify the values of global variables.
We can modify the values of global variables easily, but statics has a more secure nature than the global variables, so we can manipulate static values as easily as we can do it on global variables.
They have a security feature. Okay. Okay. Anyone else want to elaborate on this? Difference of global and static variables?
Global variables could be changed from other files also.
Okay, and where from can you change static variables?
Within the same source file. No?
In the same source file. Okay, well, let's say that you have a static variable defined inside the function. Can you access it from anywhere in that source file?
Yes.
A static variable defined inside the function.
Then no.
Kafalar karışık bu sabah. Okay, I will let you check your online sources. Global and static variables are very, very similar in terms of using them. I mean, they have what we call, of course, persistent values. Even if they do not disappear like local variables. That's the main difference between local variables and global and static variables. But the difference between global and static variables, besides the fact that they persist on their values, is that one, global variables are accessible from anywhere in the file. Any function can call them. And of course, their values persist. I mean, any function can change the value, and whoever changed the last value, I mean, that will be the last value remaining in that variable. But with static variables, variables, non-global static variables, well, in that case, you can only access them from the function where they have been declared. We are talking about the non-global static variables. So be careful. They both persist in their values, unlike local variables, but they have that difference. So anyway, let's get to the part that interests us, and that is where they take place. So let's look at our example. Here we have a simple C program. We have two header files. We have two global variables at the top. But the difference between them is that one of them is initialized and the other one is not initialized. So that means the first one, the uninitialized one, will take place in the uninitialized data segment. So it will be stored in a different place of the memory region of this process, whereas the second one will be stored in the initialized data segment. Then we have a function which contains a local variable result. It also contains a parameter x. So both result and x will be stored in the stack. And of course, the return value, always, the return value will be passed via a CPU register, always. Then we have, for instance, another function, doCalc, which has a parameter val, which will also take place in the stack. We have the local variable t, also will take place in the stack. And inside the main function, we have, of course, the command line arguments, argc, argv, the command line argument count, and of course the actual command line arguments. And since they are function parameters, they will also take place in the stack of the main function. Then we have two local static variables. Since one of them is initialized and the other is not initialized, the initialized one will take place in the initialized segment and the other one will take place in the uninitialized data segment. Then we have a dynamically allocated variable, and of course it will allocate memory from the heap. Yep, and that's pretty much it. Any questions about why these things are located in these locations? Any questions about this slide? Okay. In that case, let's continue. Here we have a more graphical representation. So this is the visual representation of the memory region allocated to a process. Now, the very important thing to remember at this stage, even before getting into the details, is the following. The addresses, they start from 0. They go who knows to where. But what is important is that the process is under the illusion that it is alone in the entire memory. The process is under the illusion, it thinks that the entire memory of this computer belongs to it and it is alone in this memory. So it thinks that if it wanted to, it could allocate all of it. So here, for instance, we have the virtual memory address as if nothing else exists in memory. So these are the virtual memory addresses. So they increase from the bottom to the top. At the bottom, at the first location, we have the, of course, text, the program code. And right after it, we have the initialized data segment. So global and static variables that have been initialized. And these, of course, are read directly from the program file, from the binary program file, and immediately transferred from the hard drive directly from the file to random access memory. And right after the initialized data segment, we have the uninitialized data segment. So the global and static variables that are not initialized at the time of execution. Okay, and they are, of course, we cannot have something that is empty in memory. They are initialized to 0 automatically by the system call that transfers the hard drive info, the contents of the hard drive file, the executable file, to random access memory. They're initialized to 0. And right at the end of the uninitialized data segment, we have, of course, the heap, which is a dynamic region of memory. And depending on how often you call the malloc, calloc, and realloc family of memory allocation system functions, not system calls, functions, it can grow upwards. So in the middle, we have the unallocated memory. Now here's some terminology. Program break denotes the end of the heap region. And at the other end, we have, of course, the stack, which starts at a certain point, and it grows downwards. And even above the stack, we have, of course, the command line arguments and the environmental parameters. So the environmental variables provided by the operating system, such as the current working directory, the path for the library files, etc., etc. And even above it, at the end of this virtual memory address region, we have, of course, the kernel mapped into Presto's virtual memory, but of course not accessible to the program. And of course, all the kernel data structures. So which tables, which files are open, which signals are supposed to be handled and delivered, which memory pages are occupied by this process, and so on and so on. The list goes on. Now, an often question that comes from students at this point is, why do we have two data segments? One for uninitialized variables and one for initialized variables. And of course, this is in the name of optimization, as it explains at the right of the slide. Otherwise, if we kept all of them together in the same data segment, so a bit of initialized variables, a bit of uninitialized variables, and so on, it would contain a lot of zeros. So every uninitialized one will be initialized to zeros, then a variable which actually contains data, then a lot of zeros, then again some data, and so on. And initialization would be slower because of skipping RAM spots. In this way, it reads directly the data from the hard drive, places them to the initialized data segment, and right after it, it places all the uninitialized data. So there is no difficulty in initializing them with zeros. It starts from the beginning of the uninitialized data segment, BSS, all the way to its end. No need to skip locations of initialized data. And of course, it would be much worse in the case of embedded programs because it would slow them down since the available CPU resources are much more limited in that case. Now, let's talk a bit about virtual memory management. Any questions so far? Okay. Now, By the way, it's 10:23. Should we get into virtual memory management? Because this is 3 slides long. We can do this in 3 slides. In 7 minutes. That should be fine. Virtual memory management. Now we will have a week dedicated to memory management. So this is just a superficial view of what is going on. So bear with me. Now, modern operating systems, of course, they employ a technique known as virtual memory management. What is the opposite of virtual memory management? Now, the opposite would be to let every process stay in some region of the memory, and let it also be aware exactly where it is. So you have 8 gigabytes of RAM, you place the process at the beginning of the first gigabyte and let the process know it. Now that is concrete memory management. Here we are talking about virtual memory management. So the process thinks that it is at location, I don't know, 1 million in the address space, but in reality, it is at location maybe 10 million. So we have false addresses, virtual, unreal, non-real addresses associated with memory positions. Why? The aim is to make efficient use of both the CPU and RAM. So it is in the name of efficiency. How? How do we increase efficiency by using this technique? By exploiting a property that is typical of most programs, and that property is the locality of reference. So a very long time ago, somebody made this observation. Most programs demonstrate 2 kinds of locality: spatial locality and temporal locality. What is spatial locality? It is the tendency, eğilim, tendency of a program to reference memory addresses that are near those that were recently addressed. For instance, in a for loop, in a while loop, in a do until loop. Very often we reference again and again variables that are very close to each other, and very often the same variables. We do not just jump from one variable that is located at position X to another variable located at a position far, far away in memory. We usually access variables often that are very close to each other spatially. And not only that, there is also temporal locality, in which is the eğilim, tendency of a program to access the same memory addresses in the near future that it accessed in the recent past. So when we access a certain variable, very often we access the same variable very soon. So it is very rare to, not very rare, but it is less frequent to access a certain variable, then forget about it, then access it 2 hours later. So very often we access variables that are close to each other in the memory, and very often we access the same variable again and again, very often. Temporally, in a temporally aggregated fashion. Let's say that you access it 20, 30, 100 times in a few seconds. And then after a while, you still can access it, but you access it repeatedly once again. So that means you don't have to keep all those variables, the entire variable set of that program in memory constantly in physical memory. So it is possible to execute a program while maintaining only a part of its address space in physical memory. It is possible to execute a program while maintaining only a part of its address space. Now, since in the next 10 minutes, for example, the program is going to focus on only certain variables that are located close to each other in memory and execute and use them, reference them frequently, and it will not reference any variables far, far away from them. Well, in that case, there is no need to allocate 8, 10, 15 gigabytes just to hold that process, even though it needs that much memory in total. Because at any given time, it only references just a few of them, just a few variables very close to each other among the 15 gigabyte necessary in order to execute it. What is the advantage? Well, the advantage is even when you want to execute 300, 400, 10,000, 20,000 processes with only 8 gigabytes or 16 gigabytes of RAM, it is perfectly possible to do it because you do not have to allocate the entire necessary memory region for that process constantly in your computer's memory for each of those processes. So you can't have them simultaneously. You can't have multiple processes which in total require far more memory than the available memory on your system, but you can still execute them. For instance, let's say that you have 3 processes that you want to execute. The first one needs 8 gigabytes, the second one needs 4 gigabytes, and the third one also needs 4 gigabytes. So in total, you need 16 gigabytes to execute all of them simultaneously, but you only have 4 gigabytes available. So what do? You allocate 1 gigabyte for each of them, since you know that they will not be using all of that memory at any given moment, and you still execute them simultaneously, even though you only have 4 gigabytes of memory, whereas if you didn't use virtual memory, you would have needed 16 gigabytes just for the processes. That's the main idea. That's the principle. The main principle behind virtual memory management. Of course, it also has other advantages, such as the isolation and security of processes. Here we have a very simple explanation of the memory pages. We will have a much more detailed explanation in the following weeks. And I will terminate with this slide since it is 10:29 and you have another course starting. Or in fact, we should stop at this point before getting into the page tables. Yeah, I believe it is better this way. So we are at slide 27. So we should be able to finish. I mean, the rest is very easy. We should be able to finish tomorrow at 8:30 with the rest of them. Any classes? Yeah, sorry, any classes? Any questions from the class concerning the slides? I'm sorry, I didn't drink any coffee this morning. Since processes will not use that much memory, what is the advantage? Well, we are not giving it to them, Mr. Arnold. I mean, let's say that they need all those, let's say that they have that many variables in total. In total, they contain enough variables and data structures that require 32 gigabytes of memory, but we only have 4. So what do? At any given moment, I'm only giving it 1 gigabyte or 2 gigabytes, just the bare minimum to keep it working. Why? Because of temporal and spatial locality. Because at any given moment, it is only using a very, very small fraction of the total amount of variables that it requires. But from a management issue, from a management perspective, since we are using virtual memory, the program isn't aware of this. The process isn't aware of this. It still thinks that all of its variables are in memory, whereas the operating system dynamically, it allocates portions of memory for this process as necessary and removes them whenever they become redundant. So in front of the curtain, you see the process, and it thinks that all of its variables are there in memory, whereas in reality, behind the curtains, you have the operating system only giving it just enough memory to keep it alive. How? By using the virtual memory pages. And we will get to that tomorrow morning. But as I said, this is more of a operating systems theory. So since this is a more implementation-oriented course, we will be more focusing on how to program in these conditions. But of course, we need to be well aware of the conditions on the system before starting to program for it. Now it's 10:31. You are going to get late for your next course. So thank you very much for your attendance, and I will see you at 8:30 tomorrow morning. Thank you class. İyi dersler. İyi günler arkadaşlar. Hoşça kalın.
Hocam Türkçe bir şey sorabilir miyiz?
Ders bitti. Artık soramazsınız.
Geç mi kaldık? Tamam.
Yarın sabah.
Tamam. İyi günler.
İyi günler.